I'm Rodger Baker, Executive Director of the Stratfor Center for Applied Geopolitics at RANE, a global center of excellence for geopolitical intelligence and analysis. Learn how you can put geopolitics to work for your organization at ranenetwork.com. Welcome to Applied Geopolitics, the podcast of the Stratfor Center for Applied Geopolitics at RANE. I'm Rodger Baker. A central tenet of U.S. China strategic competition focuses on technology. Some of this appears to be risks of overdependence upon a potential competitor or opponent for key aspects of the economy and even national security and military dynamics. Some of it is about IP and control of information and ideas, and some of it seems to just center on the sense that it's important to be better or stronger or more capable than the other. And the challenge in this field is, of course, that as we start thinking about things like semiconductors, they are integral to almost everything that we have in the world, to all sorts of commercial, civilian technology, as well as military technology. And so as we think about discussing the geopolitical dynamics of U.S. China competition, international competition, it's important to keep in mind not just the politics, but also some of the technological dynamics that will help us better understand what's at stake and understand the impacts, implications, and likely actions. So today I'm joined by Michael Hochberg. Michael is an experienced semiconductor executive and entrepreneur. He started 4 companies with an aggregate exit value of over $1 billion and exits to Nokia and Cisco, among others. He's built many different kinds of semiconductor chips, from prototype through production. He's currently a visiting scholar at the Center for Geopolitics at Cambridge University. Michael, thanks for joining me today.
My pleasure to be here, Rodger. Thank you for the invitation.
Well, yeah, certainly. And I want to kick this off. Let's begin by talking a little bit about, one, given that semiconductors are so ubiquitous, why are they not easily available from multiple alternate suppliers? What is it about the semiconductor design and production process that has left them concentrated in a few geographies?
Yeah, that's a great question. It comes down to economies of scale. When you build a plant to manufacture semiconductors, that plant typically gets set up to build semiconductors using one very well-defined process. It could be like a 130 nanometer CMOS node, or a 2 nanometers a FinFET node, or a bi-CMOS process where you have bipolar transistors and CMOS transistors on the same wafers. And these wafers are extremely complex. So, a typical wafer might have 30 layers of lithography on it, and literally thousands of processing steps that you have to go through in order to actually make the finished wafer, right? And so there are very few places in the semiconductor ecosystem where they replicate those processes between different fabs. So if you're Intel and you're operating at huge scale, you might make 2 or 3 factories where you deliberately match them together to make identical wafers in both places. But all of the smaller players don't bother to do that. And so, in effect, when you design a circuit, you have to pick a specific factory, a specific fab that you're going to make it in, because the fabs are not matched with each other. Even if they could build wafers that have substantially similar performance, like you have 3 or 4 different fabs that all make 130 nanometer CMOS, the performance of those processes is all going to be, roughly within 10% of each other. But the chip that you design into one of those fabs is not manufacturable in a different one. And so the chips are effectively locked into the fabs if you want to order more of them. And That's because these fabrication processes are so complicated that the overhead to replicate them exactly between the fabs is enormously high. You have to buy duplicate tool sets. You have to buy exactly the same tools, use exactly the same chemicals. It's just not worth it. Um, and so you're in the situation where the upfront cost of developing a process is very, very high, and the upfront cost of developing a chip design in that process is quite high. And the marginal cost of building one more wafer or one more chip or or another boat of wafers is relatively low. And so it's almost never worth jumping from one fab to another unless you're jumping to a more advanced process and building a new product.
So this brings us, and you sort of hinted at this too. A semiconductor is not a semiconductor. There are multiple different types and sizes and purpose and focus for them. Um, when we think about international competition, we keep hearing about certain nanometers is the cutoff between what is higher end technology and lower end technology and what can or can't be produced in some place. How should we be thinking about those terms, and what is it that makes a semiconductor a potential risk to national economic or physical security versus a large scale commodity type product?
Yeah, so to first order, almost none of this stuff is commodity. I'll start there. Um, even what people call the jelly bean components, which are like the little capacitors and resistors that you stick onto a motherboard that are ultimately extremely simple, old technology. Even those things are not really commodities, even though they're produced in the many, many billions of parts per year. There are only a few places that make them. And switching from one vendor to another, even when the specs are nominally identical, switching from one vendor to another, if you haven't qualified both vendors in your board design, is sort of a dangerous thing where it may break in a non-predictable way. Um, when you talk about all the different kinds of processes and different kinds of nodes, whenever I hear someone talking about chips broadly speaking, oh, we really got to work on this chips issue. What I hear is that, and this is just me as someone who's too deep in this, perhaps, is I think, do you know the difference between computer chips and potato chips? I'm not sure you do. Um, the 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 reality of this is that when people talk about these advanced nodes, 4 nanometer, 2 nanometer, 3 nanometer, what they're talking about is the most advanced digital chips. The digital world is the world where you're building chips that have billions and billions of transistors on them, where they're optimized for building things like CPUs and GPUs that are the engines for computation and the engines for AI. These are the most expensive processes to develop. A modern fab that can build those kinds of chips is tens of billions of dollars. The R&D to stand up a process in one of those fabs is, if you integrate it over the several years that it takes to do it, it's on the probably on the order of $100 billion of R&D, certainly many tens of billions of dollars of R&D, and and they rely on really exquisite precision in order to make those things. They're among the most complex things ever made by humans. Um, those chips are almost all made at TSMC. Um, but and that's the area that gets a lot of attention. But honestly, it gets more disproportionately more attention than it deserves in some ways, because most of the chips that are used by military and consumer electronics, they're often running in much less advanced nodes. The when I started in this industry, the most advanced node was probably about 130 nanometer CMOS, and those 130 nanometer processes are still running, right? They're still running in production. They're still producing circuits. And they're not just producing the circuits that were designed 20 years ago. They're producing circuits that are designed today, that are new designs, because oftentimes, if you don't need the ultra high density and ultra low power per computation that you get out of one of these super advanced processes, it's often much more economical to use a trailing edge node. So all of the old nodes are still running and are still used for all kinds of things that are important, like the control electronics in your stove, the electronics in your microwave, the electronics in electronic warfare systems, all that kind of stuff. Most of it runs in nodes that are not the most advanced, because doing a tape out into a 3 or 4 nanometer process, all in, just to do the design and run the software and get to the point where you can send the design out for fabrication. It's not unusual for that design activity in an advanced node like that for a big chip to be a multi-$100 million activity. That's just before you even get the first chip back. And that's assuming that you're working into a place like TSMC where they already have the fab and the processing figured out and they're just providing that for you. So just it's really a pure design cost. Whereas if you go into a more trailing edge node, you could be talking about, you know, a few $100,000 for a tape out, $1 million for a tape out, even less. Um, so the other thing is that chips are not just electronics, right? There are photonic chips that are used in the telecom network. There are chips that are used to make lasers. There are chips that are used for any number of different applications that are outside of just microelectronics. And in fact, if you look at it more broadly, the same kinds of infrastructure that are used to make the computer chips are also used for packaging them together. You also have fabs that are used to make things like flat panel displays and the displays in your phone, right? All of these things fundamentally are, from the perspective of the way they're made, they look a lot like giant chips.
So some of this explains why, the talk of Russia is being stopped from purchasing high-end chips, but they're buying washing machines and ripping the chips out and using them in something else that they can repurpose them. Um, when we look at the places that, say, the United States is targeting for assistance in dealing with China and managing these chips. Obviously, TSMC, Taiwan is central to that, and there's all the talk about, Taiwan's silicon shield in dealing with the Chinese. But the other two that seem to come up the most frequently are Japan and the Netherlands. Um, what is it about those two places that seems to put them in such an important position for balancing security needs or competition?
Yeah. I'll say something unkind here, which is that the thing that puts those two places in such a central position is our own lack of sophistication about this ecosystem. Um, and it's not that putting them front and center is wrong. It's just that we're going after what you might describe as the simplest solutions. And the simplest solutions are not always the most effective. Um, there's a machine that's at the heart of every fab. It's called a stepper or a scanner. The more modern ones are called scanners. And you can think of these things as being like printing presses for patterning for putting patterns of ink in, we call it photoresist, but it doesn't really matter. It's a kind of ink that reacts to light for patterning photoresist on top of wafers. And so you have the wafer, you coat it with photoresist, you put it through one of these machines, and this machine shines a light through what's called a mask, which is kind of like a photographic negative. And instead of blowing it up to make it larger, which is what you do with photographic negatives to do photographic prints, you put it through a reducing lens and you make it smaller so that you can print it onto the semiconductor wafer with really, really small features. Now, what I just described is what these things looked like 20 years ago. Nowadays, they're a lot more complicated than that. They do phase correction and multi-patterning, and it's not really a lamp. And it went from being a lamp to now it's an X-ray source for the most advanced scanners. And so you're talking about a lamp that is in effect just a few nanometer wavelength. So these things are super sophisticated and they cost hundreds of millions of dollars. And the most advanced ones are only made by a company called ASML in the Netherlands. They have established a monopoly on it because the world only needs so many of these things. And frankly, being able to get access to those is a choke point for building the most advanced chips. Um, Now you can use less advanced ones and engage in some tricks and some cleverness in order to make narrower line width chips, which is how the Chinese have released some fairly advanced chips I believe they've gotten all the way down to either 5 or 7 nanometer node equivalent. The numbers get a little hazy, but the way they're doing that is by doing something that's fundamentally non-economical. Now, the almost all of the advanced semiconductor equipment in the world is made in the U.S. and Japan and Europe. Very little is made in China, although China has been making a huge investment in trying to stand up their own ecosystem for making semiconductor equipment. Um, I don't. My personal opinion is that I don't think it serves our interests to allow fabs to be built or operated in China. We can touch on that later, but I think one good way to prevent that is to stop selling spares and advanced machines into the Chinese fabs.
If we take that another step, that gets to the idea of, okay, if the United States, as part of its identification of national security, and I think we'll have to swing back to that in a minute here as to what are the national security risks and concerns, or are they just
Sure.
economic? But if the United States wants to do that, it needs to, of course, build these facilities. It needs to staff these facilities. Um, what are the limitations in time, money, skill sets, capabilities, etc., um, that make a transition away from dependence on foreign elements to the supply chain to the United States potentially difficult, or at least put a time delay on that?
Yeah, I guess I'll start by saying I wouldn't paint it as a broad brush of foreign dependence, right? If you say we want to eliminate foreign dependence from the semiconductor supply chain, the expense associated with that would be measured probably in the trillions of dollars, and maybe not even the single digit trillions of dollars. Like it would be very expensive and very time consuming, many years. Um, but there isn't a lot of dependency on the United States adversaries for this kind of thing. Like you look at China, Russia, Iran, these are not places that export a lot of semiconductor equipment, for instance, or fine chemicals for semiconductors. They're mostly importers of tools. Now, China has gotten into the position where they're a significant exporter of various kinds of less sophisticated chips, trailing edge semiconductor chips, some memory, um, and they do a lot of packaging and assembly and things like that. But in terms of the actual tooling to stand up a fab, there's not a lot of dependency on China for that. So the dependency is on other Western countries. Now, from a skills perspective, I think that's a big issue. Like training people to be able to successfully run a fab takes a long time. It's a very specialized skill set. I think that's a thing where we still have some of those skills here in the U.S. We certainly have plenty of them in what you might call the wider West, the U.S. and our allies. Some of it we might have to import if we want to go fast. Standing up the physical facilities and buying the tools. A lot of these tools come with 6 to 12 month lead times. Some of them come with 2 and 3 year lead times. Some of the most advanced ones. Um, I think that the biggest factor in some ways is a matter of political will, which is if you want to build the stuff here in the United States and in the West, and you want to cut off the ability for these major semiconductor equipment manufacturers to sell their tools to China, you're going to massively disrupt their existing business, and they're going to lobby to prevent that from occurring because their business depends on it. And so finding ways to bring those companies on side so that they see it as a win for, or at least as neutral, for them to get cut off from selling to China, but be allowed to sell into a growing market here in the West. That's a really important piece of politics, because if those places are fighting you tooth and nail with their lobbying muscle, it's going to be much harder to actually push something like this through.
So technology has long been at the center of geopolitical competition between countries, um, and sometimes that is really about economic power. Sometimes it is about military and security power. Sometimes it's about information um, power. Uh, what is it about this industry that, over the last 10 years in particular, has taken such a central focus in the U.S. China competition, particularly from the U.S. side? What are the risks that U.S. Agencies have identified as coming from this component of either China being within the supply line of chips coming into the United States, or China being capable of obtaining or producing chips at the high end of the spectrum? And maybe those are two very different risk dynamics.
Yeah, so I could launch into a 2 hour monologue about this, but I'll try to keep it a little bit briefer than that. Um, so let's start with the economic, right? Um, if you have one country that is manufacturing chips that are not easily replaced, and they're selling them to another country, and then that other country is taking those chips and using them as a key component in systems that they're manufacturing, it creates an economic situation where the first state that's making the chips can turn off the supply of those chips and do a relatively small amount of economic damage to themselves, but produce absolutely enormous outsized economic damage to the other state. Because that chip that costs a few $100s to manufacture, and that maybe you sell for $1,000, if you pull the ability for the second state to buy those chips, the $500 million airplane that they're building that relies on those chips can't be delivered. The car that relies on those chips can't be delivered. The um, the the ship that they're building, whose navigation system requires those chips, can't be delivered. And so it being the source of chips that where especially where there isn't another place to go to get those same kind of chips made, whether they're the most advanced digital chips or analog chips or photonic chips, because because they are unique and they're very difficult and very time consuming to replace, and because and we can talk a little bit about the sort of natural monopoly dynamics around this, especially at the advanced nodes. Because you have these natural monopolies in the space, uh, you're in a position to do incredible asymmetric harm. Um, that's one big piece of the economic puzzle. The second is a competitiveness issue, which is if you believe that things like AI and advanced CPUs and advanced GPUs are important for economic purposes, that having the best AI gives you an economic advantage. Well, having chips that are 2 or 3 or 4 nodes, call it 4 or 5 years, 6 years ahead of the competition, means that to do the same computation, you burn radically less power and you get it done radically faster and at radically lower cost. And so, for training, for inference, for all of the things that are the most promising applications of AI in the commercial sphere, if you don't have access to the most advanced chips, you are playing at a significant cost and performance disadvantage. Now, we'll come back to the natural monopoly issue in a second, I suspect, but from a military and national security perspective, you have a whole different set of issues. One set of issues is hardware hacking and backdoors. There's a rich history in the semiconductor space of vendors deliberately or accidentally, and I mean both, uh, building backdoors into their hardware. So if you are using an adversary state's chips in your hardware where they were designed by an adversary state or manufactured by an adversary state, there is a good chance that there are backdoors built into them. And those backdoors are very nearly impossible to detect. In general, I would class them as being impossible to detect in a sort of deterministic way. And if you're operating on your adversary's hardware, you have to assume that you don't have any information security. It's one of the reasons that China invested such a huge amount of money in subsidizing the growth of Huawei, because any country that builds their infrastructure on Huawei's systems and with Huawei's chips in it, basically you have to assume that China has almost perfect visibility into all of the contents of all of their communications. Um, the so there's a security issue. There's also just an availability issue, which is what happens when you cut off supply, and what are the economic and logistical and military disruptions that come out of that. There's also the issue of not just information security, but attack vectors, both against individuals, against companies, and against sort of whole of society attacks. Right? If you have a phone in your pocket, right, that phone pretty much goes with you everywhere you go. It has all of your most personal data on it. It knows where you've been. If you can turn on the microphone, it can listen in on your conversations. Some people regard that as a feature rather than a bug. Um, it's got cameras. It's got a lot of capability. It's sort of the ultimate surveillance tool that we carry around in our pockets. If you're running on an adversary regime's hardware, that's an opportunity for them to inject disinformation, misinformation, to extract passwords, to extract personal information, to engage in blackmail. And hardware hacks are among the most difficult to detect and the most difficult to defend against, right? If building a software layer that makes it possible to do secure things on top of insecure hardware, I won't assert that it's impossible, but it might very well be impossible. It's definitely very difficult. Um, so there's all of that, and then of course there's the more unsubtle things like what just happened in Lebanon, where if you have something that's being put in the pockets of the members of the leadership cadre of an adversary state or an adversary regime or an adversary organization, you can build things into it that they don't know are there, like a little piece of explosive. Um, and it's not like we inspect every piece of electronics that comes across the border. So adding features, whether they're physical features or digital features or uh, 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 what you might call insecurity features, like these systems are so complicated. Like something like your iPhone is so complicated that sticking extra stuff into it, especially if you're the design authority, it's just super easy. It's super easy to hide stuff.
Given the existing supply chains, the existing sort of, as you know, as you've hinted at, monopolies of geography for certain types of production, um, thinking about cost issues and the like, is it plausible for the United States to actually cut off a third country's access? Or is it more about just adding friction and delays um, as part of a management tool rather than a full isolation from a key global supply chain?
That is an interesting question. It very much depends on the specifics of what you're trying to cut off access to. Um, if you're talking about cutting off access to manufacturing equipment, I think that's basically doable. Yeah, I mean, an adversary regime, if they're sufficiently powerful and sufficiently organized, they can do what the Soviets did and, arrange to steal one copy of a machine or two copies of a machine to try to reverse engineer it through a third party state. And they did that kind of stuff all through the Cold War. But these duplicating these machines, even if you have them in front of you, is often just as hard as building them from scratch, or at least nearly as hard. So there's a big difference between being able to keep something out in general so that an adversary state can't get enough of them to actually go into production versus creating a sort of hermetic system where they never get to see any machine, right? I mean, that second thing is ultra hard to do. The first thing is relatively easy to do. Um, the and what that boils down to is that our current export control system is wildly misdesigned. And I don't want to spend an hour talking about the export control regime, but our export control regimes are set up to control things on the basis of where they're going to be used, by whom, for what purpose, with what intent, and relies on all sorts of letters of assurance and pieces of paper. And it's really nonsensical. It's nonsensical and it's Byzantine, and it's kind of a jobs program for lawyers, but it doesn't really prevent things from getting sold to our adversaries or to places that will share the critical technology with our adversaries. And so moving to a system where that is much simpler and where the technologies we want to protect are just not sold by default to places that are leaky is going to be, I think, necessary over the coming years. When you talk about chips, you have sort of the same issue, which is, you know, because TSMC is a natural monopoly in the advanced nodes, uh, and the reason for that is that they have the most advanced IP ecosystem, which makes it easiest to design things into their ecosystem compared to competitors. It's the reason they get something like 80 or 85% of the new design starts in the entire semiconductor industry, because you go to TSMC and 90% of your chip is already designed in blocks that you can license. Whereas if you were to try to go to Samsung or Intel, you just don't have that underlying IP ecosystem. So it's a network effect lock-in. But the keeping the output of TSMC's advanced nodes out of the hands of China, if we wanted to do it, would be relatively straightforward in the sense that we could say, all right, these are not going to be exported to China, and they're not going to be exported to places that'll re-export them to China. Some stuff would leak, and the highest priority applications, which might be the military and national security applications, would get access to the chips that leak through, but it would be relatively easy to cut off the large commercial quantities from going over. Um, so, like I said, achieving hermeticity is hard. Achieving wildly high economic impact and exclusion from an economic perspective is very achievable.
And on the latter, it may, though, be a matter of delay rather than a permanent state of affairs. But in that delay, in and of itself, it can create strategic benefits and strengths for the acting country.
Yeah, I would say I would call it delay and expense, right? Because you know if you imagine that we were in a scenario much like where we were doing during the Cold War, it wasn't that the Soviets didn't make any of their own chips. They did. They were consistently 5 to 7 years behind the West on digital chips in terms of what were the best ones that they could make. But they didn't have an export industry in these things. They didn't have the economies of scale. And they were constantly trying to catch up by sort of begging and stealing bits and pieces of technology, both from making the chips and chips themselves. And that created all kinds of really interesting opportunities because, on the one hand, they were spending very large amounts of money to steal and replicate this technology. And they weren't making any money on it because it wasn't a self supporting industry, um, because it really wasn't competitive with what could be done in the West. It wasn't good enough to sell. And so it created a situation where they had to spend a lot of money in order to build something that really wasn't competitive. And then when they would steal consignments of chips from the West, well, sometimes they were stealing, legitimate consignments of chips that worked correctly and that they could use in their plants. And sometimes they would steal something that had been specially prepared for them to steal it, that would cause things to blow up down the road when they used them. Not directly in terms of being built with explosives, but in terms of being hacked in various ways. And so, you know, it turns out in a lot of ways it's cheaper to do it right, do it yourself, control the whole supply chain, and know that what you're getting is actually good material. And, chips that are actually designed by people who are loyal to you, where they don't have problems built into them. Anytime you're stealing something or buying something from an adversary, you have to assume that it might contain some surprises. And those surprises, if you're talking about computer chips that are of humanly incomprehensible complexity, those surprises can be pretty vicious.
So I think we're pushing time, but I do want to get one thought from you as you've looked at this, and you've made lots of references to, the Cold War and the Soviet time and competition on technology, and of course we are focusing on the U.S. China competition.
Mm-hmm.
What are the significant differences, if there are any, in the technological and economic capabilities of China today compared to the United States versus thinking about the same dynamics, obviously with a different level of technology between the Soviets and the Americans during the Cold War? Are the Chinese in a better position to overcome in ways that the Soviets weren't because the Chinese have made sure they've already been integrated into global economic chains and patterns?
Yeah, this is a more challenging situation in many ways. So one thing that's a difference is that at every level we are much more coupled, and that has all sorts of consequences. But I think the most dramatic consequences are that the because we're all carrying communication devices in our pockets, we are all exposed to the sharp power of adversary states in a way that you could go through your whole life as an American during the Cold War and never directly see anything produced out of Moscow. I mean, maybe some stuff indirectly through influence operations and this and that. But you log on to TikTok and you're seeing stuff that is selected by an algorithm that is programmed up and biased by a team that is owned and operated by the CCP, right? So, and TikTok is only one of many, many, many examples. So there's a lot more coupling and there's a lot more opportunities for the use of state sharp power against individuals and companies because there is so much more both information and economic coupling. Um, there are areas where, frankly, a lot of the world's expertise for manufacturing lives in China. For instance, for optical assembly, down to a few years ago, China was just the default place you went for assembling optical devices and optical modules because it was where most of the skills live. Now, a lot of what's been going on for the last few years is that a lot of both Western and Chinese companies have been deciding that they're going to do manufacturing in China for the China market and find other places to manufacture things for the broader market in the wider world. Um, and so a lot of that expertise has been slowly moving out of China or at least being replicated outside of China. But there are very powerful manufacturing clusters for everything in the semiconductor supply chain that is downstream from advanced chip manufacturing and packaging. So, all of the assembly of those packages into systems, a lot of that happens in China. A lot of it happens elsewhere too. Um, a lot of semiconductor, a lot of the less advanced semiconductor assembly, and a fair amount of the less advanced semiconductor fab is happening in China. They're also making a pretty big bid to be in the design chain, although they're not as far up the ladder in that regard. Um, but they're pouring money into this like it's going out of style, and this is a formula that China has followed in other industries. And so the question is, do we allow China, we as the West, do we allow them to follow this same formula where they essentially buy their way into being a monopoly and then end up with a chokehold on the industry? Or do we do muscular things to intervene and prevent it from occurring?
Well, I think there's about 4 dozen other topics we need to hit, but I think we're going to have to schedule that for another time. I really want to thank you for this because one of the things that's often missing in the discourse is, of course, the technical component. And therefore, as we talked about earlier, semiconductors are seen just as a thing. They're either the super craziest thing out in the universe or they are just a common thing. But really understanding the way in which companies or countries can access them, can develop them, to design them, what are the limitations, what aren't the limitations, gives a better understanding of the way in which this competition is likely to play out. So thank you for joining me here today.
Oh, yeah, it's my pleasure. I mean, look, to really understand this stuff, you have to start from design expertise and IP and software design tools. And then you look at all the things that go into the fab. Some of them are machines, some of them are masks, some of them, and the masks are very hard to make, and there's mask making machinery. You have to look at the fine chemicals that go in. You have to look at the compressed gases that are very unusual and very hard to make. You have to look at all of these inputs into the fab, the wafers, the test equipment, all of that stuff. That gets you a wafer. Then you have to look at all the things that have to be done to the wafer. You have to dice it up. You have to package it. You have to look at the places that make the packaging. You have to look at the design tools for the packaging. It's this very complex tree of things that all come together. You take those packages, you have to test them, you have to put the packages onto boards, you have to test the boards. There's there's this multi-layer, multi-step thing. And a lot of people look at it and they throw up their hands and they say, this is just too complex to understand. We can't do anything. And that's not the right attitude. This is a thing that is comprehensible. It's well comprehended by people who are experts in the field. And there are strategies to make sure that we in the West derive both economic benefits from this and national security benefits from it. But as you say, it has to start from an understanding of the patterns of detail, not just, oh, this is too complicated to understand, or, oh, this is actually all a commodity and is really simple. It's more complicated than that.
All right. Well, thank you again.
Yes, thank you.
All right. We've been talking with Michael Hochberg here. Michael is an experienced semiconductor executive and entrepreneur, and is currently a visiting scholar at the Center for Geopolitics at Cambridge University. For more risk and insight analysis, visit ranenetwork.com, where you can learn more about our suite of risk intelligence projects and solutions. That's RANE network.com. I'm Rodger Baker. Thank you for listening.